All right. Hello, everyone. Welcome. Good to see you, Mitchell, and Lindsay. And good to have you here, Zoe, Ken, and Keenan, and Diane. Great. So plan for today is to kind of move on and talk about our last chapter, which deals with cardinality of sets and different types of infinities and some interesting mathematical ideas. And so I think we're pretty much on schedule to get through the material that's on your homework assignment today. So you should be able to get going on all of it over the weekend. And then on Monday, we'll kind of talk about our last topic. And then I think we'll have Wednesday just to kind of use as more like office hours problem session, just getting ready for the exam. So I'm not planning to cover any new material next Wednesday beyond maybe just finishing up an idea from Monday's class. Okay, so FCQs, please do complete them. This goes for everybody, even students who are just watching these in your bedroom. Well, I guess we're all watching them in our bedrooms, but watching them on YouTube, maybe not live. So if you're listening out there, please do complete your FCQs. I'll put the link in the YouTube, in the description below the YouTube video. And if we get 80% response rate, like I said, we'll get some extra points on the last exam. Since I sent my email out in the morning, we've gone from 26 to like 35%. So we're trending in the right direction. So thanks for your responses. Okay, so what you guys kind of read about, we're thinking about cardinality, number of elements in a set, and kind of thinking about infinities and kind of categorizing how large certain sets are. So to get started today, I want us to take a look at poll everywhere. I just want to get a sense of what you guys think about these. Okay, so for those that are kind of coming in, getting situated, we're kind of just doing a little stretching to get things started today and just thinking about all of these sets of numbers and how big they are relative to each other. And let's take a look at the responses here. So we have a tie for first, it seems. We've got the set X and the set of all even numbers. We're tied for first and second. So I'm just going to record this on my iPad, and then we can kind of come back to the PDF. Okay, so yeah, so these were the responses that you guys had. And so if we're looking at all of these, only one of these sets is actually finite. Right, so the cardinality of set 1 would be 100. That's a finite cardinality. And then if we look at some of these others, all of the rest of them are infinite. There's an infinite number of things in those sets. And so the question is, are all of these infinities like created equal, or some bigger than others? And so something like this and this, which were, well, I skipped over the even ones, but if you look at these two and you compare them, you might think that 6, well, I guess you guys thought 6 was bigger than 2 overall, but looking at these two sets, right, the natural numbers are 1, 2, 3, 4, all the way up. So it seems like the number 1 is included in that set. The number 1 is not included in this set, so it might seem like 2 is bigger because it includes 1 as well as 2, 3, 4, all the way up. But actually, we just say that these things have an infinite number of elements. So they would be the same. And all of the rest of these things have an infinite number of elements. However, they're not all the same infinity. So 6 and 2, these two would be considered countably infinite. And we'll define what that means down below.
as well as some of these others. So I'm going to just circle all of the things that I'm kind of boxing in green. They actually all have the same number of elements. Whereas the three things that I haven't circled, these are also infinite, but these are bigger infinities. So there's actually more real numbers in between 0 and 1, as there are all real numbers, actually. There's no difference between these two sets. So I think there's some counterintuitive stuff here. You would think there's more numbers between 0 and 1 as opposed to all numbers out there, but actually, mathematically, we consider these the same. And we don't consider these the same, although they're both infinity. So I want to kind of unpack some of these ideas. And so these took a long time to kind of develop and civilization to wrap their head around the idea of infinity. So we call them natural numbers because that's pretty much what people started doing math with. And even 0 was kind of a abstract concept for some people. It's kind of hard to picture something that's not there. It's much easier to count things that are there. And so this idea of infinities, it's about 100 years old, maybe less than 100 years old, and people started exploring these ideas. But any questions so far before we delve a little deeper? You might have some questions about, well, why is this infinity different from that? We'll get to that. But any other thoughts that you guys have? Okay, so in general, we say that two sets A and B have the same cardinality, which we write as, these look like absolute value symbols, but again, remember, they're when we have a set inside, then it becomes cardinality. We'd write cardinality of A equals cardinality of B if and only if, and this is why we spent some time thinking about bijections last time, is if there is a bijection from A to B. Then we would consider those sets have the same cardinality. So all of the things that I circled in green up top, we should be able to find the bijection from one of those sets into any other of those sets. So for example, based on what I have above, we should be able to find the map, say, from the integers into the natural numbers, which is a bijection. And we'll show that. And that's going to prove that, okay, Z and N have the same cardinality. Whereas if I wanted to think about mapping the integers into the real numbers, there is no bijection that exists here. So they would not have the same cardinality. And these are not easy things to do. It's really hard to kind of say that there does not exist any possible bijection between these two sets. That takes a little bit of, you need to be careful about that. Okay, so with all of these different types of cardinalities, we can kind of think about them in three levels. We have finite sets. Those are great. We can count things. And then we have infinite sets, which are sets that are not finite. So we say a set is countable, first of all, I should say. Oh, okay, no, I have that down here, so that's fine. We say that a set is countably infinite, and some texts call that denumerable, so these terms are used interchangeably. If it has the same cardinality as the natural numbers. So we kind of use our natural numbers as like, this is our smallest notion of infinity, if you have the same amount of stuff as there are natural numbers. But this is an infinite amount of stuff over here for the natural numbers. So if we have a same cardinality as the natural numbers, so in other words, oh no, if I can find a map from my set A into N, which is a bijection, then we say that A is denumerable or countably infinite. That would be telling us that it has the same cardinality as the natural numbers. And since there are kind of different levels of infinity, we give them different notation. So the kind of, when something is countably infinite, rather than just say infinity like we did up here, these are different types of infinities. So we would say that those sets that I circled in green above, their cardinality all is aleph naught. Okay, so this is aleph. This is the first letter in the Hebrew alphabet. And then we have aleph 1, aleph 2, aleph 3, and they go up. So if a set either has the same amount of stuff as the natural numbers, or if it's finite, then we call it countable. So countable includes infinitely countable or finite. So so far, we've got some new terms in terms of finite and countable and so on. So any questions about that terminology?
What would aleph 1 or 2 denote if it's, what would they denote?
Yeah, so aleph 1, we'll see, is going to be like the real numbers. And then we have even larger infinities than that, and they get classified as aleph 2. So you can think about how you do that is you can think about R is aleph 1. What if you think about the power set of R, that has even more infinite stuff, that's aleph 2. And then if you think about the power set of R, then you start jumping up by degrees of infinity. So it's real interesting stuff. It's a whole branch called set theory in mathematics, which is really interesting stuff. You might have heard like Gödel's incompleteness theorem and things like this are all kind of playing a role in set theory, and power sets and all these things have a whole lots of applications. You might not think that these abstract things are useful, but they actually are in some cases. Okay, so any other questions, sorry, before we start taking a look at some of these examples? So what I kind of want to do, I think the way things are lined up today is to kind of show all these green things that I circled are the same infinity. They're all countably infinite. And then next time we'll take a look at the uncountable stuff, which is a little bit trickier. So first claim here is we want to show that these sets are countable by showing there exists, and here, if we're showing there exists a bijection from n to the set. Sorry, I wrote my bijection this way, but typically we write it the other way. We go from the natural numbers into the set A. But if it's a bijection, right, we can do it either way. Sorry. So this is what we really want to show. So if there is a bijection from the natural numbers into the set, we're not just getting countable here, we're getting countably infinite. So when we want to prove that something is countable, the method again is to construct a bijection from the natural numbers into that set. Okay, so we can take a very basic map there that says it's the identity map. So I don't think this is pretty much how we start defining countably infinite, right? Is we kind of start with the natural numbers. Okay, great. The natural numbers are countably infinite because I can just create a very basic map from the natural numbers back into themselves, which is injective and surjective. So I will kind of leave the details of like justifying why this is bijective to you, but you can kind of go through and show it's injective and surjective. Any questions about that one? Okay, so next up is the even number. So now it's not quite as simple. The identity map is not going to work. But the idea is we've got a set of natural numbers. And we'd like to see, is there a bijection F that's going to map this set to the even natural numbers? Any suggestions about finding a map that's going to work, that's going to do that?
Well, when I think of an even number, I think of 2a. So maybe a function like 1/2 of a will give us back a.
Yeah, so keep in mind here, when we're doing this map, we're starting with the natural numbers as our domain, and we're thinking about this set E as the codomain. So I think you've got the right idea. But if I want to go from natural numbers into even numbers, I wouldn't want to divide by 2, right? Because I might get things like 1/2 and 3/2 and so on. But for example, what I can do is take and map 1 over to 2, 2 over to 4, 3 over to 6. And what are we doing when we go in that direction? You guys pick up on the pattern for that?
Just doubling.
Yeah, so we're going to map A to twice A. So if we want to kind of formalize this a little bit, we define our map, and then we would show it is a bijection. But I will leave that for you guys. That's not, I don't think that's too big of a leap of faith to believe that that's a bijection there. And there are other ones that could work too. So these are not unique maps. You probably can construct some other ones as well. Okay, and so yeah, so you'd want to check, you know, 2 different inputs should not get sent to the same output. That checks, it's injective. This map is going to map to every single even natural number. That checks out, so it's surjective. Okay, so in this case, we went from a set that maybe seemingly has less stuff than the natural numbers, right? We kind of popped out all of the odd stuff. And we saw that even though this has like seemingly half as many numbers as this, okay, they're both countably infinite. So we would consider those 2 sets as having the same cardinality. And 3, it's a slightly different scenario in that now we're going from the natural numbers into what seems like it might be a larger set of numbers, right? You might think that there are more integers than natural numbers because we've got 0 and all of the negative stuff. But to prove this, same idea, we go from the natural numbers. Sometimes it might help to just write out these sets. Okay, now the problem is we're going off, we're not bounded in either direction. So any ideas here? So we need to somehow get negative stuff and positive stuff here, right?
Well, you can let at the beginning of natural numbers 1 equal to 0, then for 2 you go to +1, then 3, -1, and keep going alternating.
Okay, so we can send 1 over to 0. And again, these are not unique ways of doing it. So if you're thinking about something else, that might work too. So I think a good place to start is just like start mapping them, right? And what happens in math is just picking up on patterns, on how things work. So the suggestion here was to take 1 and then map that to 0. Kind of take like the first natural number and map it to kind of the baseline for integer. Then we could take 2 and map that to 1. We could take 3, map it to -1. We can take 4 and map it to 2. We could take 5 and map that to -2. And I think you can see here that if we kind of stay the course here, I think this should work. We don't have a formula for it at this point, but I think that process seems like it could work, right? That each number is going to a unique thing function. 2 different inputs are going to different outputs. So it seems like it would be injective. And this is going to give us a way to map to every single integer. So it seems like it should be surjective. So let's just kind of write this out, and then let's see if we can find a formula for this. So we're saying 0 is going to 1, or excuse me, what am I doing? We don't even have a 0 here. Right, so we're going from the natural numbers into integers. So we're saying 1 is mapping to 0, 2 was mapping to 1, 3 was mapping to -1, 4 was mapping to 2, 5 was mapping to -2, and so on. Let's think about it like this. Seems like we've got different things going on for the even and the odd natural numbers, right? Seems like we've got outside of 1, seems like the even these kind of even integers seem to be going to the positive things, and right, the odd integers are seeming to map to the negative integers, and we're sending 1 over to 0. So any thoughts on what the map would look like for the even integers? 2 goes to 1, 4 goes to 2, 6 goes to 3.
Just positive natural numbers.
So yeah, so the even things are being mapped to the positive integers. So for example, 2 goes to 1, 4 goes to 2, 6 goes to 3. So for any value a, what's the formula for how to find out the integer that it's going to get mapped to? Yeah, so we've got 1/2. Thanks for that. So hopefully you guys can pick up on a pattern like that, right? So 2 goes to 1, 4 goes to 2, and 6 goes to 3. So we've got, we're taking the even number, dividing it by 2, but we're still staying within integers, right? Because those are even things. And that's going to allow us to hit every positive one. Then for the odd ones, right, we should be getting something negative. So I should have a negative sign in there. So then we see a pattern here. 1 goes to 0, 3 goes to -1, 5 goes to -2. So it seems like we have, again, a half here because we need to take these odd things and map them over to negative things. I don't want to just divide by 2. That's going to give me something which is not an integer. Yeah, thank you. So if we do something like this, that would then fix the problem, right? So now if a is 1, that checks out that we get mapped to 0. If a is 3, then we get 3 minus 1, which is 2 over 2. That gives -1, and so on. So this one checks out as well. So then what would be left would be to first construct this function and then prove or argue why this is a bijection. Any questions?
Is this a situation in the surjectivity where you would get something like C equals and then something on the right and then argue that there is some value of C for every A?
Yeah, so if you did want to do surjectivity, right, the idea is to show that the range and the codomain are equal. So you pick anything in the codomain, pick any integer, and then you would have a case, right? I guess you would have case 1, C is positive, right? And then you would use this thing. Case 2, C is not positive, and then you would kind of set up that thing. Yeah, but you would need to take it in separate cases because the function is defined differently depending on what the input is. Okay, so let's set up some breakout rooms and give you guys some time to try one of these on your own. So let's think about 4. And here again, we want to show that this is countably infinite. This set T is countably infinite. So that means we would like to find a function, a bijection from the natural numbers into the set T. And you don't need to kind of in your groups go through the proof of injective and surjective unless you want to, but think about how you can construct a function, and maybe there's more than one thought that comes up. And if you wrap up that and you want to start thinking about 5, feel free to go for it. But I think we'll kind of think about this one in groups, and then we can come back together and kind of knock out some of these other ones. So let me set up breakout rooms. Okay, so how did 4 go for the group I was not in? Good. What was the map that you guys came up with? Someone in that group?
Just A plus 1.
Okay, yeah, we did the same. That seems like the natural way to go for that one. Any questions about that? Was the other group able to get going in question 5? A little bit? Okay, that's better than, and I think we got thought about how to prove this map F was a bijection. But let's think about this over here. So what I'm writing out, right, are the natural numbers over here, and here's n cross n. So this might seem kind of crazy that they're the same amount of things, but there actually are. And the thing that we need to be comfortable with is here we're going to show what the process for this map would look like, but I don't think we're going to be able to find the formula for that map, but that's okay. So what we can do is just like do what we did up here. Say, okay, I'm going to map this one to this one. I'm going to map this one to this one. And even if we don't have a formula to describe that process, but if we can in words describe what that process is, that should be sufficient. So I'm going to map, for example, this one makes sense. Let's map it to our first order pair over here. I'm going to say f of 1 is 1, 1. Okay, then I'm going to map f of 2 over there to 2, 1. So I'm going to kind of start over here. I'm going to go down, and I'm going to go over to 1, 2. So the next one I'm going to map is going to be f of 3 is going to map over here. So pretty much all I'm doing here is saying, here's 1, here's 2, here's 3. And then once I hit this top row over here, I come back over here, and I'm going to just go along these diagonals. So I'm going to say f of 4 is equal to 3, 1. F of 5 is 2, 2. F of 6 is 1, 3. And then that puts me up here. And then I come down to the next diagonal and I work my way across this one. And then the next one, and then the next one, and then the next one. So we kind of snake our way through all of these. And this process is kind of like a snake theorem here, kind of slither our way around through all of these pairs. And in this process, we can see that we'll hit every single ordered pair, and we'll hit every ordered pair exactly once. And each natural number is getting mapped to a unique ordered pair. So this tells us that n cross n is countably infinite. And in fact, this result can be generalized, in fact, to say this, that if we take any two countable sets and look at their Cartesian product, that result is going to be countable. So I believe this theorem isn't in the book. So you might just want to check out how the general case goes there. So we could have proved this theorem and then used it to claim this, right? Then we could say n is countable, so n cross n is countable. Any questions about that? Okay, and so we're kind of building our way up to showing, I think we had a bunch of stuff at the start. We had 7 things that were countably infinite, 3 or countable, 3 of them that were uncountable. So I think maybe the one that might be surprising is that there's the same number of rational numbers as there are natural numbers. And to get there, we'll first find the map from n into rational numbers. And here, I can sort of think of the positive rational numbers sort of as a subset of n cross n, where if I take a fraction a, b, so if I have a and b integers, and in this case, we're just dealing with positive numbers. So if I have 2 natural numbers, a and b, then I can think of the rational number a divided by b as like an ordered pair. So now when I want to come up with this map from the natural numbers into the positive rational numbers, let me write out the these elements. So I've got my natural numbers, and instead of writing 1 over 1, I'm going to write that as the ordered pair 1, 1. And I'm thinking about 1, 2 as 1/2, 1, 3 as 1/3, and so on. And then we can use the same process, which is, okay, great. F of 1, that's going to be the first ordered pair, 1, 1, which as a fraction, right, that's just 1. So we're going to map 1 to itself. And then we can come down to this one. This one is the next one. That would be 2 over 1, so that's 2. And then we go, so here's kind of like the first one, here's the second one, here's the third one, and we'll kind of snake our way around the same way. But it doesn't work exactly the same, right? And what's the issue that we've already run into here?
You got 1 twice.
Yeah, this is not bijection because this is not injective. We have 2 different inputs at this point, 1 and 3, that are getting mapped to the same output. And that's because, you know, as an ordered pair, this is different from this, but when I take their quotient, right, we get the same thing. So we have this extra subtlety that we need to worry about. But because we're not writing a formula, we can just describe this process and say, if we get an ordered pair, which is equivalent to something that we've already hit, we just skip it. So then I'm actually not going to map 3 here. We would come down to the next row. and say, let's use this as the third one. And say, okay, we haven't gotten 3 yet. That we can use. We come over here to, I think I did this wrong, didn't I? I would go from 2, 1 up to 1, 2. I don't know why I crossed this one out.
When you're talking about elements in a set, I know that 2 over 2 mathematically is equivalent to 1, but is 2 over 2 as an element of a set different than 1 over 1?
So we're talking about rational numbers here. So I'm not thinking about these as ordered pairs. I'm thinking about them as quotients. And some of these ordered pairs are equivalent to others when we think about quotients. So 1 over 1, I would treat the same as 2 over 2, because when I divide those two coordinates, we get 1 in both of those cases. Yeah. So in this case, we were considering all of these pairs unique. 1, 1 is different than 2, 2. When I'm thinking about these pairs as rational numbers, then they're not all necessarily unique because we have different ways that we can write the same fraction. Yeah. So we just want to say, okay, we're going to treat all of those fractions the same way. I messed up my weaving through this stuff. Sorry. I don't know if you guys caught that. This one is fine as 3. We haven't hit that one. And that's how we hit some of these rational things. And it's when I would get to the 5th one is when I would hit my first repeat. So this, right? So we would start at 1, then come here, then go up there, and then come into this third diagonal. And it's along this third diagonal when we hit f of 5 that we get 2, 2. That's equal to 1. We've already hit 1, so we skip that element. And then we just jump up to the next ordered pair, which I think is 2, 3 or 1, 3. And that gives us 1/3. So that's how the map works here. So in this way, each natural number is going to get mapped to a distinct thing, and we're going to hit all of the positive rational numbers. Okay, any questions about that? Sorry about my mess up with that one the first time.
So for these kind of problems, you don't always need to have an equation, right? Like there's
That's
not
right.
always.
Yeah, so sometimes we can have a formula, and when you can do that, obviously that's really nice, because then we could say, okay, where does like the natural number 105 get mapped to? Oh, it gets mapped over here. In this case, you know, I wouldn't know exactly which ordered pair 105 gets mapped to, but I do know it gets mapped to something, and that something is different than all of the others. So that's the kind of thinking here. Yeah. So sometimes you can give a formula, and sometimes we can describe the process that's going to work.
Should we expect to need to disprove the fact that a set is countably infinite by proving it either fails a bijection or surjective quality?
So if you
Like, are you gonna ask us to prove that the real numbers is countably infinite or disprove it?
Yes, we'll get into that next time. So today we're just thinking about countably infinite stuff, and then next time we'll think about uncountable stuff. And that's right. If I want to prove that the real numbers are uncountable, then what I need to show is that there's not a possible bijection from the natural numbers into the real numbers. Yeah. Okay, so finally, here's this last result here. So we are kind of ticking through this in about an hour, what took people about 1,000 years to figure out. So that's pretty good timing. is now let's try and extend some of these previous ideas to prove the rational numbers, all of them, positive and negative ones. And so in this case, I'm not going to kind of write out a lattice here of all of the negative stuff too, because we would have like a big mess of stuff going in both directions. But so far, what we do know is we have a bijection F. That's the one up here that we kind of wrote out, that goes from the natural numbers into the positive rational numbers. What I would like to do, right, is have a map that goes into all of the rational numbers. So I'm going to define this function g, let me put it like this, as a composition where we go from the natural numbers into this using this map f that we talked about above. And then we're going to compose that with another function that goes from the positive rational numbers into all rational numbers. We'll call that h. So this function g, right, is the composition of first go from the natural numbers into the positive rational numbers. Then we'll find some map that's going to take positive rational numbers and map them bijection into all rational numbers. Okay, so any thoughts about, we've got F already done. So what I'd like to think about is, well, how can I then, after I map into the positive rationals, then map that into all rational numbers? So any ideas that we have come across that might help us do that?
It's kind of like problem number 3, where we went from, alternating from positive to negative.
Yeah, it kind of looks like this, right? Here was a case where it's very much the analogy, right? Except not the cross product now. But like going from n to z seems like a pretty similar, like taking the non-negative stuff and then suddenly mapping to everything seems pretty similar. Like, okay, we're going from the non, or at least from the positive rationals to all of them. So let's pick this up. Maybe it'll help us on all of it. And let's see if we can use it down here. Good idea. But we'll have to tweak it a little bit. So here we're going to define this function g. So we're going to do this whole business over here. And we'll define it again, like separately, whether things are even and odd. So we're going to take a, and we're going to map a into either something positive or something negative, and then map f of that number. So this is going to take the natural numbers and map it to some positive and negative things, and then we take and apply that function f to that result. And sorry. And we say if a is odd, then we map it to the negative one. We're going to use a equals even to map it to all of the positive rationals. where this map F is from number 6, and kind of this map over here is similar to what the process that we did. I think that was number 3. Yeah. So what we've seen is that we have, like, we called E the set of even natural numbers. Right? That's contained inside of the natural numbers. And the natural numbers, well, these are contained in, even put an intermediate thing here, right? These are a subset of the integers, which is a subset of the rational numbers. So we have, even numbers embedded inside of natural numbers, embedded inside of integers, embedded inside of rational numbers, but the cardinalities are all the same. But this chain doesn't go on forever. So there's this distinction, is we're not just thinking about, is this thing a subset of the other thing? But what we want to think about is there a bijection from the natural numbers into that set? If so, then it's the same cardinality as the natural numbers, which is why E, Z, and Q all have the same cardinality. If we can't find one, then it's not. And we'll see next time that this is uncountable. And we'll kind of see how we can prove that. And it's not easy. It took us a while today. It took us the whole day to get through and show that the rational numbers are countable. So it'll take a little bit of work to get through proving R is uncountable. But on your homework assignment, you don't have anything about uncountable sets. So it just goes up with countable things. And now I realize there's one point to make that is on the next worksheet that might help you on this homework assignment. You have a question that says P and Q are countable. Then actually, I think it's P. To prove that that is countable. Okay, nope, you're good to go for that one. I'm trying to remember. There's one question there's one thing I want to let you guys know. I know what it is, but I want to let you know. I'm trying to remember what the homework question is. But we said that if you want to show that set A is equal to set B, has the same cardinality as set B, then you want to show that there's a bijection from A to B. Sometimes we want to show, and you do have a question on your homework assignment where it's not A and B, but you're comparing two sets, and you'd want to show that the cardinality of one is less than or equal to the other. And in that case, we still want to consider a map. I'll give it a different letter. We just want to show that that map is injective and not surjective. Okay, the surjectivity would give us equals. You have one question where you're asked to prove that one set has a cardinality which is less than or equal to the other set. And in that case, that map that you construct just needs to be injective and not surjective. But we'll talk about that next time too. Okay, so that's a wrap for today. Got 2 minutes out early, so if you haven't done your FCQs, use that time to complete your FCQs. Otherwise, have a nice rest of your week. We've got office hours tomorrow. If you do get started on, if you've already started on the homework, feel free to come by and let me know if you have any questions. Otherwise, I'll see you guys next week on Monday. No reading assignments due next week. So for Monday, just come and we'll talk about uncountable stuff. Okay, thanks everyone.